today is, as of now, this is going to be our last video here. I might come back to the series later on in the future if I have like more deeper topics and that to talk about. But for now, this is the end of our other book. And so after this, I'm probably, at least like I said, at least for a while, we're not going to have any more videos in this series. But we're running on a nice round 120, which is pretty cool. Today we're talking about Cartan's theorems. And throughout this section, we are going to be working in the context with K. In this case, it's either going to be real or p-adic, actually. We're not considering the complex case in this context. And the reason for that is that so the rationals are dense in K. Well, we get our first theorem here. We're going to write two theorems in corollary all at once before we go through the proof of any of it, just for kind of pacing's sake. First off, we're going to suppose, first theorem, suppose G is a Lie subgroup over K. And that H in G is a topologically closed subgroup chunk. Then H is analytic. We have a corollary to this, which states that a closed subgroup of a Lie group over R or p-adics is a Lie group. And we have a second theorem which states we're going to have two Lie groups over K. Then any continuous homomorphism phi from G1 to G2 is analytic. And so our proof. Step 1, we actually want to show that theorem 1 implies theorem 2. So since we are operating on the assumption that phi is continuous, the graph gamma phi in gamma 1 times gamma 2 of gamma is a closed subgroup. Oops. Hence, by our first theorem, this graph meets the conditions of our first theorem, and since we're assuming our first theorem, the graph is going to be analytic. We're going to let P be the restriction of the first projection of G1 times G2 onto the graph of phi. making it an analytic homomorphism with a trivial kernel. Thus, its algebra version is injective, and we have that P is an immersion. So P is an analytic isomorphism. Then, of course, this gives phi as analytic, as it can be written as the composition of the second projection with the inverse of the first, of this first P. You know what I mean. Alright, so now we just need to show our first theorem that any topologically closed subgroup chunk of a Lie subgroup is analytic. So we're going to split this over two cases. First, we're going to show it in the case of the p-adics. So here we are going to give our algebra of Rg explicitly, and by taking a small open subgroup of G, we can assume that G is isomorphic to an open subgroup U of G under the Campbell-Hausdorff formula, and that H is a closed subgroup of G. And from this we can identify G with U. Then for X and H and N and Z, we have that N on X is going to be Fn of X in H. As H is closed, the same, we can generalize N to being a p-adic integer. Now we're going to choose x1 through xm in H such that they're linearly independent over QP and maximal with this property. We're going to let V be the vector space generated by the xi. Then x has to lie within V, since otherwise our xi would be not be maximal. And now we can prove it suffices to show that H contains a neighborhood of 0 in V. First off, we consider the map F from ZP to the M to V, defined by F of T1 through Tm as the product of T1x1 through Tmxm. Then F is analytic, and D of F at 0 is bijective by construction. So F is a tau at 0. As the image of F is within H, H contains a neighborhood of 0 in V. Alright, so now we need, thirdly and finally, our last step is to show we have our first theorem when our base field is the reals. Once again, we're going to let G be the algebra of our G, and we can assume H is a closed subgroup chunk of U, where U is on a new page, where U in G is an open subgroup chunk under the Campbell-Hausdorff formula. You can also assume H is strict in U, which means that if X and Y are in H and their product is in U, then their product is in H, and if X is in H, then its inverse is in H. We're going to then let V be the X and G where T times X is in H for small, sufficiently small t. This is going to be the points X and G such that an interval about 0 on the ray through X lies in H. Then, well, we have a lemma we need to show in this case, which has two simple parts. First off, V is a Lie subalgebra of G. And secondly, suppose that Hn is a non-zero element of H. Xn is a non-zero element of H. And we're going to let Dn be the line in G containing x to the n, x sub n. Suppose that x sub n goes to 0 and d sub n goes to d as n goes to infinity. Of course, then we hypothesize that d is within V. Alright, I need to prove this now. We're actually going to prove the second part first. Secondly, we fix epsilon such that a ball of radius epsilon about 0 is contained within U. Let m be a positive integer and epsilon sub m be epsilon over m. We define each SI to be the x such that the absolute value of x is between I minus 1 times epsilon m, and I times epsilon m. And that is a closed interval, of course, which will of course make S1 be the ball of radius epsilon m. And you can see from this definition it's just going to be like the annuli, would be the word, of successive multiples of radius epsilon m for some constant k to the m. We have x to the n lying within S1 for all n at least k to the m. As for some k to the m. Now we want to consider some value I such that I is greater than 1 at most m. Then for all every n being at least km, there exists an integral multiple. Actually, we need to name it first. Called yn to the I of xn, which is going to be in Si. Since dn converges to d, a subsequence of yn to the I converges to a point in S sub I intersection D, which is also going to be in H since Yn. The i's all live in H, and H is closed. Hence, for any positive integer m and I being greater than 1 and at most m, there exists an x in H intersection D such that the absolute value of x lies within between I minus 1 epsilon m and I epsilon m. Thus, H is dense in at least one of the two half intervals of length epsilon with endpoint 0 in D. By part B from above, or previous, H is dense in the symmetric interval of length 2 epsilon about 0 in D, and it's actually going to be in H intersection D since H is closed. Thus D has to be inside of V. And then we're going to show our first part, if I can get this to scroll properly. And we wanted V to be closed under addition in brackets, of course. So we're going to let x and y be in V, both be non-zero. Then by the Campbell-Hausdorff formula, well, there's two things to show here. First off, I mean, we don't need to show these are by Campbell-Hausdorff, but to write the limit as n goes to infinity of n of 1 over n x times 1 over n y is x plus y. And the limit as n goes to infinity of n squared, I think this is supposed to be, yeah, of the same 1 over n y is going to go to the bracket. Thus, the lines through x plus y and x bracket y satisfies certain desired conditions. Since V is a Lie subalgebra of G, V intersected U is an analytic group chunk of U under the Campbell-Hausdorff formula. Under the assumption of strictness of H, we see that H contains the intersection of V and U. So we are done. If we show that H is contained in V in a neighborhood of 0. On the contrary, suppose we have a sequence x to the n such that x to the n is in H but not V, and x to the n goes to 0. And then goes to infinity, of course. Choose a W to be a complement of V in G. Since the exponential is a local isomorphism at 0, we can write x to the n to be Wn times V to the n with Wn and W V to the n in V for sufficiently large n. By strictness, Wn is in H for large n. So we can assume the original sequence x to the n belongs to W. I'm going to let then dn be the line through x sub n by the compactness of the projective space P of W, a subsequence of our collection of d to the n converges, say, to D. But then D would have to be within V, which is a contradiction. And alright, we have one more mark to finish off this whole series. So we've shown that the category of Lie groups over K being real or p-adic is a full subcategory of the category of all locally compact topological groups. So then, when is a locally compact topological group a real or p-adic Lie group? And because we've seen that if the structure of a Lie group exists on a locally compact topological group, it is unique. And so we actually have answers for all these. In the real case, G must contain no small subgroup, which is saying there's a neighborhood U of E of the density such that any subgroup of G contained in U is equal to just the identity itself. And that was by Gleason, Montgomery, Zippin, and Yamabe. And in the p-adic case, this is by Lazard, the group G must contain an open subgroup U such that, first off, U is a finitely generated pro-P group, and secondly, the commutator subgroup U comma U must be contained in U to the P squared, which is the set of P squared powers. And yeah, so that's actually a good, I feel like that's a good kind of basis for get a good base understanding of Lie groups. I'm going to be working on homework and then probably my thesis pretty soon. So that's pretty exciting. Hopefully this was this might actually end up being somewhat informative of a series to someone. Like I said, maybe later on I'll come back to the series with a more advanced, nuanced understanding of it. Right now I'm still learning, but I enjoyed this series. I hope you did too. Thanks for watching.